how is it going to relate to the rest of the world and where does it scale ahead? And to do so, we assemble people from a variety of different perspectives to give you some insight into how different people are thinking about this problem. So this is the set of panelists. I've asked them to speak for no more than 4 minutes each. So we're going to do total 16 minutes, and then it's your job to come at them with as many questions as you possibly can for the next, well, however much time you have left over. We really have an hour, hopefully with some feedback. So the first person is going to be Mario Valente. I met Mario a couple years ago when he was in Wisconsin, and I had no idea that I was going to catch up with him in California. So he's a physician scientist who's had human longevity. And then we're going to move forward to Patty Sophia, who is a program director at the National Human Genome Research Institute. And then we're going to, she's going to give you insight into what's going on in the NIH and what their challenges are that they're facing. And then we'll look at things from a legal ethical perspective about blocks. And then we'll bring it back around from the security perspective with Kurt Roloff, and we'll talk about a little bit of applied global crypto and the challenges of making it work in practice. So without further ado, we'll start with Malia, and then we'll move forward from there.
So I was asked to explain some of the medical aspects, and I think the first thing to communicate is what are we going to protect. I think we need to understand what needs to be protected. And this is a concept that maybe not everybody has in mind. It's that what we are thinking we are protecting is the pathogenic variants. And actually, this is a minority and something important. Today, I think we have 60 actionable variants to protect, and then maybe endemic disorders. And actually, each one of you carries around 2 million variants. And most of them are rare or unique. So that means that what we are going to protect, for the most part, is something we don't know what it means. Which is very interesting because it means that we are right on time. So basically, right now, the official recommendations as of March 5th from the American College of Medical Genetics that we all use is that the variants are classified by some criteria as pathogenic. By likely pathogenic, this is almost purely computational, uncertain significance, and unlikely to be pathogenic. And also there are some that are already denied. But basically, of 2 million variants that you carry, only very few in the dozens are something that we know something about. And this is a very important concept. The most famous word today that you have to learn is RUS, that means variant of unknown significance. And this is something that we are missing, is that everything is going to be trading and asking for variants of unknown significance across platforms. So I thought that I would say what are issues on how to annotate and associate cerebral disease means that as variants are pretty personal or rare, maybe 5 in 50,000 people, 5 in 100,000 people, we will be trying to find who are those people so we can compare. There's no longer large cohort statistics. Here we're talking about how to find a phenotype to attribute to that variant that we find in few places around the States or international. So it means that we will have to be hopping between multiple databases and centers and maybe countries, trying to say, has anybody seen this before? And does it have any particular trait associated with it? If you have a cohort, then it may be, for example, a multiple sclerosis or Alzheimer's cohort. You will be getting metadata that is very personal to that question, and it's likely that whatever variants will not match the ad hoc information available. So another concept for rare variants that we carry will be to try to find individuals to call them in again and phenotype precisely or extensively. That's another no-no in privacy. How can we make the way that we will be able to re-phenotype people if we really want to understand gravity? So the challenges to privacy from this standpoint, and again, it's the standpoint of the fact. That means that we will need to understand variants of unknown significance that are by definition rare and dispersed across databases, hospitals, countries. So we have to look for those people. That means we have to understand how to pull these people out and ask questions pertinent to this variant. We will need, of course, some secure protocols that allows us to crawl in databases and pull maybe not the genome from people, but that variant, what's the associated phenotype for that given person. And then more and more, and I'm a true believer on the concept that the human genome will have to be solved by the human population. I believe very much that this will end being the individuals themselves will want to explain their own genome. So we'll have to face more and more people with particular variants that will try to find similar people around to try to explain their own rare variants that they are carrying. So these are my 3 slides. Again, I hope that you think that your protocols will have increasingly to pay attention to not how to protect huge crowds, but how to protect the queries on very precise variants on very precise individuals.
I'm Anna Sophia. I'm a program officer at NIH and Human Genome. I've been the science officer for iDASH for the last few years. I want to tell you first off that privacy is very important to NIH. It's part of the foundation for the biomedical research enterprise because without protecting patient privacy, patients would lose trust. And right now, patients have a pretty high level of trust. They trust their doctor, they trust that the system will protect their information, and they mostly want to make a really active contribution to solving human health problems and contribute to research to help do that. So patient privacy is important to the patients, and it's very important to NIH. So the genomic data is a challenge for privacy. It's now been declared and as part of policy that genomic data is intrinsically identifiable. There is no real fundamental way to de-identify genomic data once you have any significant amount of it at all. It's a true fingerprint of identifiability. So it means that unless you have explicit consent to release it, it's often has to be kept under controlled access. So the NIH policy that governs this is called the Genomic Data Sharing Policy, and it was recently updated just as of the end of January from the previous policy that governed this, which was often referred to as GWAS policy. And so the Genomic Data Sharing Policy, or GDS, it has some changes, some important differences from the previous GWAS policy, but mostly the idea is to extend both protection and sharing across a wider collection of data to make it, to make it more modern, try to make it more modern. But clearly incremental changes and a lot of carefulness about how to do this in ways that help share the data, but also really maintain this value of protecting privacy. So it's actually important to realize that only some genomic data falls under NIH GDS policy. And so international data, data that's not been produced by funding from NIH is not controlled under GDS policy. International data, some countries have rules that are more permissive, some countries have rules that are more strict, and also data that many collections of data might be controlled, they might be produced by commercial or nonprofit entities that are not connected to NIH efforts, and they may be data that's controlled falls under IRB or Institutional Review Board control. So a fraction of the data has particular rules that I can describe to you, but a lot of data does not. So it's actually important to keep that in mind. So a couple of additional challenges with genome data, in addition to the privacy aspects, are well, not just genome data, but data important to biomedical research is the complexity of the data and all the different data types that you really want to bring together to make sense of it. So to really interpret genome data, you want to bring in all of the clinical data, you want to bring all the other types of molecular data, the other omics, epigenomics data. You want to bring in image data, you want to bring in signal data, there's important sources of text data, and you want to be able to work with it all together. And of course, bringing data together increases or makes more complicated the challenge of keeping it private. But this is especially important in the context of the new initiative that was announced recently, the Precision Medicine Initiative, to be able to bring a complete focus on an individual with all different modalities of information that you can develop so that you can develop the best healthcare choices and develop the most powerful research directions in a precision medicine context. So the other challenge is scale, but actually the challenge is more of growing rapidly rather than absolute scale, because even the largest sources of data in the biomedical context, which tends to be genomic data or image data, is growing quickly, so it breaks all the available toolkits, but in absolute terms, it's not huge, it's not enormously large for big data. It's just large for biomedical researchers. It's not really large compared to data scales that physicists deal with for astronomers or commercial interests. But it poses challenges in terms of being able to do the things that biomedical researchers need to do. And then part of that, again, is the complexity of the data, how to deal with really messy, fundamentally messy data a lot of times. So I want to illustrate some of these ideas in the context of a particular project that I think serves nicely to illustrate some of these features. And this project is it's a cancer genomics project called the ICGC TCGA pan-cancer analysis of whole genome sequences. So this is a pooling of data, international data, including about 50% is US generated and falls under NIH rules, and about 50% is international and falls under a separate regime, regulatory regime, that's controlled by the ICGC consortium. And so this data, since the goal is to analyze it all together, to pool all the cancer data for 25, 30 different tumor types together to learn about cancer as a whole, as opposed to individual tumor types, and then recomputing on the data to remove any batch effects, and then reanalyzing the data for the purpose of, for this particular purpose, especially with emphasis on non-coding regions. This is obviously an international consortium, and the rough scale of it is a total about 5,000 whole genome sequences. And so that's about a petabyte, perhaps, of data, order of magnitude, a petabyte of data. And to do this is beyond the capacity of any individual group to do this. So what you're looking at actually is a map showing the places that have donated major compute resources to be able to do this analysis. So it's about 20 different countries participating, but about 6 different compute resources that are being pooled to do this uniform analysis of this relatively large single collection of genome sequences. And so you see there's participants from Asia and Europe and the United States, but given the 2 policy regimes that govern this single unified data, the policy regimes being the international side and the US side, what that means at the end of the day is that international data can actually be computed on the cloud. So the resources donated by Europe and Asia and the United States are being augmented with that half of the data set with use of Amazon Cloud. So Amazon Ireland and Amazon Oregon. But that can't be done with the US data. The US data is not allowed to be on the cloud because of the GDS policy. And if you did it, if you accidentally put it on the cloud, there could be fairly severe consequences to doing that. It's an enforced policy at this time. But it's the same data under 2 different policy regimes. So it shows up the additional complexity in addition to the scale and the complexity of the data itself, having operating within the policy regime that governs the use of the data appropriately. So just to finish up quickly, tools are being ported to the cloud. There's a lot of interest in the cloud, .cloud. It's an analysis toolkit developed by University of Michigan that's being designed to work with large-scale data on the cloud. And it's not the only one, there's other examples. And there's a lot of interest in using the cloud, a lot of pressure to be able to use the cloud. Actually, although the policy doesn't currently allow that, it is under active discussion, and it may be a work in progress, what rules govern putting this data on the cloud. So that's it.
My name is Doug Fox, and I'm from the University of San Diego School of Law. I'm going to be speaking without slides this afternoon. We've all heard a lot about the enormous promise of genomic medicines and technologies. But that promise won't be realized unless a lot of people aren't too worried about issues of privacy or security, about discrimination with their genetic information, to be willing to share it. And yet, genomic data can be leaked by a reckless physician, by a clinician, by a disgruntled employee, and it can be de-anonymized. And even data that is stripped of information that would be able to connect it to a particular individual are what Dr. Sophia called intrinsically identifiable. Melissa Gimrick and her colleagues, in an article recently published in Science, demonstrated just how easy it is to connect genomic data for which the identifiable information, most of it has been removed, to connect it with the person from whom it came. And because the genomes of individuals can reveal information not just about those persons, but about people closely related to them, that information can tell a lot, not just about the person whose data has been given, but also about their siblings or about their children, the kinds of sensitive information that we've been discussing. And this is true whether that genomic data is disclosed maliciously or accidentally, or whether it's given voluntarily. Now, these privacy risks can have serious consequences for people's lives. The information can be used to establish paternity or parental status and family disputes. It can be used by police to identify suspected criminals or relationship to suspected criminals. And of course, be shared with insurers or employers who have interest in the health status of individuals. The United States Supreme Court has not established a constitutional right to informational privacy that it has said applies to whole genome sequencing data. What we have instead is a patchwork of legal and regulatory mechanisms that provides significant but incomplete protections against genetic discrimination and what many would regard as violations of privacy. For example, the Genetic Information and Non-Discrimination Act, known as GINA, prohibits the disadvantaging use of genetic information by employers or health insurance providers. But it doesn't apply the disadvantaging use of that information to disability insurance or life insurance or long-term care. Nor does GINA have anything to say about privacy concerns like use or access or disclosure of genetic data. Now, these kinds of privacy concerns are addressed most significantly in another federal law, commonly known as HIPAA. This is the Health Information Portability and Accountability Act. HIPAA forbids certain entities, health insurance providers, and similar entities from disclosing information that can be connected to particular individuals, patients. But that law doesn't even make clear whether it applies to genomic information, as among other kinds of health-connected data. Nor, and this is the case even after the High-Tech Amendment in 2013, Does HIPAA extend to those entities that most commonly manage public genomics research projects? And here I'm talking about federal agencies, academic institutions, or scientific consortia of the kind that Dr. Sophia mentioned. These entities are bound instead by the somewhat lesser protections that are afforded under the so-called common rule, at least here in the United States. This rule requires that human subjects research, that which is funded by the federal government, that is, obtain informed consent, minimize the risks to participants where possible, and get passing marks by institutional review boards. But this common rule doesn't apply either to research that is funded either by state governments or by private citizens or organizations. Most importantly, neither HIPAA nor the common rule imposes any restrictions on the use or disclosure of information that doesn't identify an individual or provide what's referred to as a reasonable basis upon which to identify that person. This is, of course, at odds with the new conception of genomic data as intrinsically identifiable. Of course, it's held that de-identified data is unprotected under HIPAA. That's a federal law. Now, state governments here in the US do provide some additional protections. That is, in the 19 states that do offer those protections. But these are spotty and patchy and don't provide for a minimum floor across the United States. So what does this suggest? Well, for people who want to participate and contribute to genomics research studies toward the pursuit of new therapies and other technologies that would benefit humankind, well, they should do so informed of the risks and benefits, not just the known ones, but also unknown ones, including the risk of incidental findings that might arise from the data that they've shared. And what this also suggests is the great importance of trying to achieve genome security, which is, of course, the reason why we're all here. Thank you.
Hi, everybody. My name is Kurt Roloff. I'm currently an associate professor at NJ. Mike?
There's people watching you on webcast.
Okay, good. So my name, that sounds very loud. Is that too loud?
Yeah, it's pretty loud.
Okay. All right, I can control my enthusiasm. So my name is Kurt Roloff. I'm an associate professor at NJIT, Computer Science. And it sounds like it's quite a lag to the voice. Is there actually people hear that? Which thing?
It's okay.
That's okay. Okay, good. So I'm actually coming to NJIT after several years in industry. In particular, I was leading the implementation team for the Dark Proceed program, which was a government initiative to develop secure computing technologies, particularly secure multi-party and homomorphic encryption. And so I'm working on implementing and adapting and looking at the deployments for homomorphic encryption for the past couple of years. And in particular, software and hardware implementations, MATLAB, C, C++, and FPGA. And it's been actually a lot of fun looking at initial applications and have some initial work on that. But somebody just made the jump to NIT and academia. I'm starting to look at lessons learned from these various approaches. And IBM's done a lot of great work with this implementation. I'm particularly proud of the work that we did for DARPA, and I know Microsoft did some really great work also. And one of the things that we were just talking about very much is the need for something next gen. What does it mean to have an API design for greater usability, accessibility, and whatnot? Get some sort of standards out there. Particularly, I'm going to come from the technology angle and bring this back to the policy. Just bear with me for just a couple minutes. 3 minutes now, I think. And so, what are the rolling open source development we're going to be doing? So, we're starting to do some of that in NJIT. Try to take these initial work that we've all been doing, and what's the next step to make it more usable, more accessible for general computer scientists, that can start to then partner with people who own applications like geneticists and physicians. So we're going to be working on this, and I'm actually trying to put together a community of interest that's interested in software engineering aspects, particularly computation, particularly last crypto and FHG. So I encourage you to send me an email. It's right there. You know, one of those things about having unusual names is very easy to find online. So, but this actually gets at some of the open source issues of how do you actually go and build software from a software engineering perspective. And it's all about composition to a certain extent. And so we have these FPG operations, and I'm a particular fan of NTRU-based approaches, but I know IBM has their more BGP-based approach, and I know Microsoft has a variant of NTRU also. But you have basically nothing else other than software layer that you can use to make calls to encrypt, decrypt, and so on and so forth, up to bootstrapping. And well, then you have a fairly limited list of crypto operations that you need to support, particularly for FHE, and similar also for secure multi-party. Particularly for FHE, has things like transfer transform, the ring operations, and sampling and whatnot. And from there, actually going then and making calls down to particular things like CPU code, FPGA service, C libraries, and whatnot to run that implementation. And so this is actually what we do with software engineers. So we try to make these things extensible, usable, adaptable. So, for example, if we were to think about bottom two layers as effectively being most of HE-lib right now, putting another layer on top of that and actually make calls to bootstrapping and so forth was part of the work that we want to do to make this more usable and whatnot. So, well, what does that actually mean for privacy management? What does it actually going to mean for folks that actually want to use private computation for things like genomics? Well, when you think about these kinds of systems, what do we have? We have these what we call messages, real numbers, emails, ASCII text, JPEG images, genomic data. Well, what we do is that we go and code that information as plain text. And I might be abusing notation just a little bit, but please bear with me for the time being. And so we go things as plain text, and effectively right now there's strings of odd integers, vectors, nothing else. At least they look like computer scientists. And then we go on encryption operations. So we do things like put things in the ciphertext, strings of odd cube integers, depending away on your CRT or double CRT type representations, and then run computations on that data. And when computations are done, you push the ciphertext back into plain text with the encryption operation, and then go decode operation. And so what we worry about was computer scientists. We worry about, or at least low-level systems people, we care a lot about the things on the far side. You know, if you're facing at the right-hand side of that diagram. And then we leave a lot of the, and then we leave, thank you. And then we leave a lot of the other operations for people that want to go and use it. And so this is one of the things that we're particularly interested in focusing on is aspects of, okay, so we have these use cases and we have these various messages. And a lot of the work that we're seeing today, a lot of the kind of differences between the various teams that have been presented in various results, is how do you know in code, what kind of data structures you actually want to do, and what kind of values. And so part of me thinks that, okay, we come as a software engineer, standardization, extensibility, adaptability, we're starting to get our hands around some of the issues about the encrypt and decrypt operations, so we have these common APIs. Well, there's also, we start looking at these albums who might mean by, for example, what do we mean by distance? What kind of computations do we want to start use? And although this is a little more tenuous right now than we might think about for the FPG type operations, I obviously see a lot of the needs for things like encoding, decoding, and whatnot, data structures being ongoing also. So, without further ado, I think I'm pretty close to my 3-minute limit, so to speak. So, thank you very much, and I look forward to joining the panel.
We've got a couple mics, we've got a couple experts. I think you can tell there's a diversity on the panel. So does anybody want to kick us off? If not, I will kick us off. All right, Kevin.
I can have multiple questions. The first question about the, this is very interesting. for the you just mentioned that you have to log data both from US and from outside the country, right? And well, for the DNA data from other countries, they are allowed to be analyzed in plain text on Apple EC2. And so I'm just wondering, just for the donor of those data, have they signed this open consent or whatever, or those countries simply don't protect those data at all?
I'm sorry, the daughter,
The person who donated the DNA data, right? Have they all signed open consent?
No, it's not. It's not open consent. It's not open consent. It's a different consent regime. So it's not public access. It's still controlled access data. But even with controlled access data, with NIH controlled access data, you can't put it on the cloud. But with the ICGC controlled access genome data, you can put it on the cloud. So it's still all controlled access data.
But in this case, will the cloud service provider use that kind of agreement?
There's definitely a business associate agreement that's been signed. There's negotiation with the cloud provider.
Okay.
But at the end of the day, it's still a commercial cloud. So it is protected. It's generally believed to be safe for this computational analysis, but it's just different results from different policy and regulatory groups with a different take on the situation, at least at the current time.
So it's very interesting. So basically, you're talking about for NIH, right? Even there's some agreement, and which has been signed by the commercial cloud. We're still allowed to put the data.
At the current time, but this is under active discussion. So that's a good question for policy.
Shouldn't you consider the infrastructure where you hold this data, your addressment? So basically, any infrastructure where you put data, it's a liability.
Certainly, if you haven't taken care of all the security aspects, privacy is a layer on top of security, and so there's no such thing as no risk. And it's not to say that that a particular cloud is not much safer than some poorly managed cluster. So there's a separation between actual security and actual privacy and the policies that have best intentions for ensuring that there's security and policy. I'm not sure I caught your question.
Well, I was leading into, if we assume that whatever infrastructure, database, whatever, in this database residing on, and any infrastructure that will perform computations that we want it to perform, there should be a protocol for verifiable computation as well, a protocol for interpreting data, because ultimately I would like to have my own key for the data or my genome. So only the things that I want to be performed.
That's right. And so technologies that provide all these just different capabilities, that's what this community, as represented in this room, is really suited to develop. And there's a huge need for it in NIH and other biomedical research arenas. And so we really need these communities to come together and provide all these different aspects.
So let's spread this around the panel a little bit. Because
Yeah.
I heard the term risk used by every single person. I heard people talking about variance of unknown significance. I heard people talking about risk with respect to security, risk with respect to discrimination, risk with respect to NIH policy and oversight. And so the question that I guess for all of you is, so at what extent do you see either, where do you see the limits of both the technologies as well as the policies? So for instance, with variance of unknown significance, if we only have 1 or 2 or 3 people with such variant, can you ever have privacy if we're going to claim that things are not yet unviable, right? And to what extent could you ever protect such an individual? Is that possible, right? So what are the limits of such protection?
So I think that's a mathematical question that means those three individuals still have huge amount of diversity. So this unique variant is hidden behind the great complexity of the rest of the genome. So I think it's a question to this community of how to identify an individual just on one variant, and what are the risks into that. So I just posing that as a challenge that we need to solve if we want to solve the genome. Basically, we have to go one by one, understanding each one of the variants, and this will put us in this context of how do we approach these three individuals, and we obtain their metadata.
So to play down on, I still want to know about, where you see the limits of your technology or policy or scientific perspective.
Maybe I don't quite understand the question to a certain extent. Are you talking about more in terms of use as an individual type user, or are you talking about more like most level national policy, or where are you getting that?
So I'm posing a practical challenge that means we know that we will need to jump across different data sets with different levels of protection or with different levels of access to try to retrieve people not on the genome, but on one variant of the genome, plus the metadata. So how does that scenario fit? What is usually discussed is how do we move 4 genomes across and how do we compete on full genome? This is the contrary scenarios. How do we compete and move for one variant and still face the same challenges of privacy?
I don't know. I frankly don't really see that as much of an issue all that much. I think it's more the case of, if they build it, people will come. And I think it's a matter of, this is fairly standard, not too hard to do in current engineering practice nowadays. It's more the underlying security technologies and the crypto systems making sure it actually runs fast enough. And one of the major precepts of cloud computing has always been to the point of, partially it's been outsourcing computation to someone so you don't have to manage your own infrastructure. That's kind of what we're doing here with all these problems, outsourcing data management. Well, one of the other large benefits of it is that instead of moving your data around, you put your data all in one place and move computation to the data itself. And so this fits in with a lot of standard cloud infrastructures that are out there right now. Infrastructure as a service, data as a service to a certain extent also. And I think the challenge might just be more, so I spent a fair bit of time looking at applications, trying to convince people that this stuff should be usable. And I think it's more of policy limitations as much as anything right now, to actually have that kind of model. Whereas right now, a lot of things are protected more by legal agreements, regulation, and more pieces of paper and trust issues as much as anything. And one of the benefits of these kinds of technologies is that, yeah, you should be able to circumvent or even subvert a lot of these kinds of grievance policies, subvert very, very positively. But at the same time, it seems like a lot of policymakers have not come to the point where they necessarily trust it. Maybe we shouldn't until there's some sort of ISO or FIPS standard associated with that. But as far as the technology itself, you can make it run fast, you can make it scalable, but a lot of the underlying information infrastructure is sometimes bread and butter.
So let's go all the way down to law. And as we're going down to law, as we follow up on this question, let's focus in on discrimination issues in particular. Mainly because I'd be curious to know your perspective on to what extent we should permit discrimination. Mainly because this is the whole point of having differential insurance premiums and the fact that we don't necessarily all constitute the same amount of risk. So if you do have individuals that bring about more risk in the system, why do we protect them to the same degree as others?
That's a great question. In large part, we regard genetic information as something worth protecting. It's worth protecting because we don't choose it. It's worth protecting because we're all subject to its consequences, and it's something that we conceive of as sufficiently personal, private, and intimate that it is an inappropriate basis upon which to discriminate among people. That said, of course, it has some consequences for industries and practices of interest, and most especially in the insurance context. I think that our discrimination protections need to be strengthened significantly. But this depends in large part on how it is that we conceive of genetic information. We could, I imagine, in the future, imagine it as being something less personal, more widely shared, more freely disseminated in a way that would make those protections less crucial. But for now, I think our protections need to be strengthened. As to your first question about risk, I think it's a very difficult problem. Most importantly, because those risks are unknown, they're changing. And what do we do about that? Well, there are two models that different genomics research types of research projects have proposed. One model that is used by the HapMap project and 1,000 Genomes project is it requires reconsent. And that is, well, we inform individuals at the moment that they choose to participate by sharing their genomic data. We inform them of the existing known risks and benefits, and then they can make a decision about whether they wish to share. Then when we learn new risks and benefits, then we will require reconsent. We go back to them. And if they're alive, if it's possible to track them down, and we acquire that consent all over again in light of the new information about those risks. Of course, that's extraordinarily expensive, not always possible, but that's one approach, is to continuously update consent to make it informed in light of our new knowledge about the changing risks. A different approach would be to say, well, that's too difficult, or not practicable. So the approach that's been adopted by the Personal Genome Project is called open consent. And it basically makes no privacy guarantees whatsoever. And they instead try to inform participants and also cultivate their participation to a limited extent and allow them to have certain control over access over their data. But at the end of the day, say, hey, the truth is we can't protect your information. We can't guarantee your privacy. And the existing discrimination protections or anti-discrimination protections are what they are. And you, at the end of the day, take responsibility, and we're not going to make any greater assurances than that. And that will play on people's civic responsibility and sense of participation and willingness to go for the greater good, notwithstanding the risks, unknown and otherwise, that may lie.
So I have a lot of perspectives. I'll hold them all to myself, and I'm going to give Dan the floor.
To follow up on that a little bit, in Europe there's a discussion on whether encrypted information is personal information. Encrypted personal information is still personal. So could I make a survey among panel members on how you feel about this? Because this result highly impacts the kind of work we in the technology community do. Because, for example, also the same last point we touched on regarding consent, if it's not personal information anymore, we have different kind of work. We can start from, I would love to have everybody's perspective on this, so we can start from whichever end.
That's fine, it's not controversial.
So it is my hope that encrypting would allow people to get away from too many restrictions. That's my hope. My hope is encrypting as a facilitator of research. And now is this legally breached out of this difficulty? That's what I don't know. But I would think, as you, I would hope that encrypting would mean, yes, we can, all of us, we can do operations of this data across borders.
So, Dan, great question. I know we've talked a lot about this one-on-one over many years. So I know I use the same arguments I always have with you. You have this kind of similar question, so I'll try to throw you a curveball, respond in a slightly different way. That, whereas the technology itself is fascinating, exciting, growing, important, and justifiably of interest, at least for me, and hopefully everyone, I would turn a little bit to say that a lot of it really depends on how this technology is going to be put in context. Whereas, you can contradict myself slightly in the conversation you just had briefly about how a lot of the underlying infrastructure is kind of bread and butter. But one of the distinguishing aspects, particularly if you look at encrypted computing technologies, serial multi-party, FHE, whatever, It's about use case, adversary models, so on and so forth, writ large. And whereas FHE is really good for example, outsourced computation, which is cool and all as long as you don't necessarily share keys. And unfortunately, to do FHE being practical, sometimes you might have to share a key with whoever might actually use it, as you do in things like functional encryption. Things get a little easier, like you get a guy to functional encryption work, secure multi-party, I'll be a little better than that. I know you probably enjoy it when I say something like this. So, but in a certain sense, I think you're exactly, maybe this is what we're getting at, that how you want to share the results of the computation is going to matter quite dramatically, and how you might want to set up the information structure and for aspects of sharing keys so you can actually get access to the things that really matter.
I would say that if you encrypted the data, that it's if you've encrypted the data, that for all intents and purposes, it's genomic data, but it's a de-identified form of genomic data. If you've encrypted it and it's not possible, at least with the current state of the art, to identify the individual, that for all in practical sense it is de-identified, which is an amazing technology. But one concept that maybe governs this area is that it's actually important for us to be upfront with the idea that you can't eliminate risk. It's not that you can hope to eliminate risk, but what you strive for is to achieve the right balance between risk and benefit. And to eliminate risk, you can spend infinite resources and then end up with a system that's not useful or practical or doesn't do anybody any good. So it's important for us to be upfront with patient participants that there may be some risk, and to make sure that they actually understand that. And as far as eliminating a certain kind of risk by the personal genome approach, it's very useful to have these genomes available that can be computed upon. Just like 1,000 genomes, genomes are a very useful data set. But for the purposes of biomedical research, they're actually not that useful, because there's such an extreme selection effect on the people who are willing to share their data in that fashion that you end up not being able to study the things that you want to be able to study. That's such a strong predeterminant.
So we're not actually talking about privacy, and I think your question brings that up. We're talking about anonymity. And the difference is this. The privacy has to do with sharing the personal, sensitive, consequential kinds of information. And privacy protections say, I don't have to share that personal information about me, or you can't take that kind of information, or you can't share it with others, but you know who I am. It's just that personal, private, or sensitive information will not be shared. Anonymity, instead, is what's at stake here. It's importantly different insofar as you know the personal, sensitive, consequential data. No one's suggesting that not be known. That's the whole purpose of what we're doing. It's the reason why it's so valuable. And what's unknown instead is just the individual. It's just the person that information connects to. And so when you ask whether encrypted data is really personal data, or whether it's really whether we ought to subject it to privacy concerns, everything hinges on how good the encryption is. I agree that the balance of risks and benefits ought to be conveyed honestly to patient participants, and that it's up to them to make that decision, and that the risks will never be null, and that the benefits will be great. But I'm not as comfortable with saying that encryption is good enough for the here and now, or under our current state technologies, or given the protections that we can afford it today. Because of course this information will live on, and it will connect to us long beyond whatever this current state of protections is. And so unless we have confidence either that data won't be used in adverse or disadvantaging ways against us, or that we, like those here in this room today, will be able to fight the good fight and develop countermeasures to de-encryption or de-anonymization, re-identification, then that is a great risk that needs to be communicated to patient participants, indeed, not one to be taken lightly.
So The gentleman from New Jersey would like to rebut, and then we'll get back to the NIH rebuttal.
Wow, this person never been described as a gentleman. Thank you.
Esteemed colleague from New Jersey.
Much more accurate, making us sound esteemed. So you're actually making a really, really interesting point about the issue of what is the privacy issue, how do we communicate these kind of things. So maybe this is something that we have to deal with as technologists, about communicating. We have these technologies, and they're not all one and the same. They're all quite different. They have different kinds of privacy models, and I might have alluded to this earlier in Dan's response to Dan's question. Is that, for example, mobile encryption is an outsourced type operation, so that if you share the result of, if you share access to a result of a computation, it means you also share access to the original source data. There's other ones, for example, functional encryption, which I mentioned in passing briefly, which is because you share the result doesn't necessarily mean you need to share the inputs also. And this, I think, is going to be probably a really important aspect of the technologists need to be better, more communicative, more effectively communicative of these kinds of things where, yeah, encryption is cool and it does provide a lot of protection. But if you want to use it, there's other ones, different, there's a spectrum of approaches. You might be able to throw in a problem. Different ones have different privacy trails, ethical trails associated with their use, and we're not even doing a good job of communicating this to folks who are leaning in our favor. And maybe that's just something that we just need to do better.
Well, I agree with you in a lot of ways. I guess I would point out that, you know, some of the strongest drivers for sharing this data are the patients themselves. And so people who have a fatal tumor, they're frustrated often with the data being locked up. They've given their data, they want it to be used. And so they know they're going to die, but they want this to have at least some small meaning. They want to make their contribution. So they're often the loudest voice for sharing. The other point is that, well, you know, is this, you know, being from human genomes, sometimes we're accused of genome exceptionalism. So, you know, we're so careful, as we should be, but we're so careful with genomic data that at the same time, you know, is genomic data more sensitive than financial data, or the three-dimensional data picture that is developed for everybody, that follows you, you know, through every web browser that you touch. This picture that's being assembled by data brokers and being sold for commercial value, and yet people are extremely unaware of that. Why should there be genomic exceptionalism? So why not be more straightforward with the cost and benefit in a more three-dimensional way, although it gives some very interesting ideas.
Go ahead.
So I asked the same question at the guy who is the works on fundamental rights in the European Commission, Directorate General of Justice. So I didn't get the nice answer I got from you. Exactly what was voiced to me was that we need to keep on showing how these technologies that we develop help in particular settings and show these privacy guarantees, how they are achieved in each particular setting. So I'm very happy that this is a challenge for us and we will have to tackle this somehow. The question is explaining encryption or any kind of adversarial models to lawyers. I've been doing that for a while. It's been hard. People design similar protocols.
So let's play us out a little further. Okay, so let's play this out a little further. No, I'll talk loud. It's fine. One of the challenges that I think we all keep coming across is that there are these barriers. There are barriers that exist between technologists, lawyers, scientists, practitioners in the clinical domain, and so these interdisciplinary relationships that facilitate research and what works and what doesn't work. So sorry, that was not a good sentence, but to what extent can the NIH or other agencies, whether it be commercial or whether it be not-for-profit, facilitate better interaction between these communities to develop integrative approaches that address the type of privacy issues and security issues and trust issues that we're really talking about here. I think personally, one of the challenges I've run into is that it's difficult for the NIH to fund foundational work in technology development. And it's difficult for the National Science Foundation to fund application-oriented work in the healthcare domain. So to what extent can this occur? Do we have opportunities? Sorry. Getting hyped on this spot.
Well, I just know one institution that is devoted to this very kind of work. Most presidents, well, at least since Bill Clinton, appoint a committee that is devoted to bioethics. And their role is to advise the executive branch on issues in that area, but also, and I think perhaps even more fundamentally, to bridge these different institutions, these different kinds of people from various backgrounds, to try to make clear the details, the risks, the promises that are at stake, that are difficult to understand to people from a legal perspective, ethical perspective, technological, scientific, industrial, and so forth. And President Obama's committee, called the Presidential Commission on the Study of Bioethical Issues, just a couple of years ago released a major report on just these questions, on genome privacy. They spent a significant amount of time studying these issues and releasing their recommendations. I think that
was a consensus report.
It was a consensus report, but I think what's unique about it is that it is meant to educate people from various backgrounds, and one that I think can be a point of departure from which to begin, and only just begin, that conversation that is so important.
So I'll take this maybe slightly also from a technologist perspective. So I'm a big fan of these kinds of challenge activities, and so I would applaud the organizers of this workshop in this regards. But one thing I'll also challenge you guys back, something I think might be just missing a little bit, is the aspect of we're running operations to show computing on encrypted data. Where's the red teaming? Where do we show we can operate these things? Where do we take the, for example, results of this computation, and that we've had a certain number of folks on cryptanalysis on the computation itself? And I would debate a little bit that the various solutions that were posted are at varying security levels and different protocols, and they have various security trade-offs. Maybe something really exciting would be to take the entrants this year and put them out there as, hey, another aspect of the challenge is, can you crack us for next year or future years? And start to look at those kinds of things also. To start to develop, from a technology perspective, a level of trust in that things actually work, that they're implemented, they don't have side channels, and those kinds of things. But like I said, technology is a solution to a technology problem.
I think this is interesting. I think this is an extremely dangerous thing to do on the version of field. Because right now, all of you are sitting in a situation where nobody wants this technology that's sitting outside this room for the most part. You're screaming at people to adopt it, but you're proposing, you're proposing security technologies and you're trying to solve problems that it's very difficult to provide evidence for that they exist. And that's one of the challenges. So if you start poking holes in the solutions that you're bringing to the table before people are even interested in using them, I'm sorry, you're shooting yourself in the foot. I mean, it's a good thing to do, but you really have to do this in a tempered way.
But at least, I think this is a very good suggestion. It is at least the one thing we can do is we're looking at the different security guarantee those techniques can provide, like different animals model, and particularly bring the people just like dog, and basically telling us, whether there's any practical policy and legal means to support those adversary model, right? And one thing I always want to talk to a lawyer is, and there are a bunch of folks who is very interested in, and they're very extensive research in this kind of technique, which is called secret sharing, right? It's a very intriguing technique. So the idea is I can outsource my data and computation to multiple parties. Each party does not have the full picture. Each party has no information at all. But if these two parties collude, they can recover the whole data. So I just really want to understand, what is the legal, implication of these things? Because on one hand, the data owner loses the control of the data. On the other hand, those individual parties like IBM and Microsoft, right? And then they don't get any information unless they collude. So, so in this case, so what kind of agreement you need to sign with them? And just what will be the legal implication here? So these are very extensive techniques used by different research groups, right? Just in this competition, we have at least 2 teams using this technique. And they are very vibrant research in the security cryptography community. But based on this assumption, the things could be extended. You can have just a small group of people. If they don't collude, then my scheme is secure. But if they collude, you lose everything. So in this case, what can you do from the legal and ethical viewpoint? What kind of agreement you need to sign with IBM, with Microsoft to make sure they don't collude?
So I just wanted to go back to what you said, that we are producing solutions that nobody wants, which actually, and I would say also, I think it's also up to this community to produce practical applications that will reconfort. For example, if a genome is sitting in a hospital, how does the encrypting facilitate actually the interaction of a given doctor or a given service with that genome by using all these protection layers? And I always use as example the pharmacy. The pharmacy should be able to call into a stored genome and ask for a question that can only be limited to one simple thing: can I give this drug or not? And this avoiding that this pharmacy enters in any other part of the private sphere of that genome. So I think it would be important that the community also sells applications to convince people that this is not just Star Wars and protecting large databases from large attacks, but this is a day-to-day, how do I access the stored genome in a way that does not leak beyond what is supposed to do for that function in that query.
This is a really important point, that to the extent that if you can play out this even further, it would be even better. Because I think one of the challenges that people keep seeing is there's different aspects here. There's the research side and the application side. And on the research side, it's all bent towards discovery. And when you're bent towards discovery, you don't necessarily know what it is that you're working for. When you're working with researchers, they want to touch the data, they want to feel the data, they want to have some interaction, formulate hypotheses as they're working with it. Whereas when you're on the application side, you have a service, and you can turn that into some type of a very standardized formula. So you get access to this for this purpose. I think you're in a much safer zone for the design of security technologies. That doesn't mean that you shouldn't have security or privacy for research. It's just, I suspect it's going to be a much more difficult road to walk down. Comments?
Just in response, the current legal protections in the United States that are provided under HIPAA, under the Common Rule, and under all state laws that I know of that protect genome privacy, protect just non-disclosure. That means certain entities blanket cannot disclose. That means to anyone. I know of no laws or regulations or rules that say you can't disclose to the people to whom colluding would impose a special risk of a privacy breach. Or you can share with some people, but not others. Or you can share only in certain ways. Or if you share to these people, there are special penalties, really large punishments. You could draw up a law like that, and it's not so unheard of in law generally. Thinking of antitrust in some other areas, although it is unprecedented in this area. I know of no current regulations that would operate in just that way. So we'd have to think creatively as lawyers in order to think up solutions that would allow researchers and participants, incentivize them namely to continue to share and to produce the kind of work that we want, while affording the sorts of protections that we would need in these special circumstances you described.
I don't know, I didn't know that. Okay, so are there any other questions from the gallery? Are you all completely enamored, ready to go off and solve all the problems that the world faces? Okay, so if that's the case, I think to try and get us back into where we were, then let's thank our panelists. And I'll turn the mic over to
Actually, okay, thank you. So we are going to the next section, which will be section 2 for the presentation from participating teams. Our first speaker is from University of Maryland, Fahid Aya, and the young team is the winning team for the task 2.1, the first task of the challenge 2. Good afternoon, everyone. I'm Karthik Naik, and I'm going to present a solution to develop using Oblivion. To join me with Xiaowang, Changliu, Yang, and my guest Shi. So before we go on to solutions, there's a framework that we developed as and we developed a solution on top of this. This is a programming framework for secure computation, and some important features of this framework is that it's very easy to use for non-specialist programmers. They develop something like a C-like language, and we provide security guarantees. The framework efficiently compiles programs to circuits. So real-world programmers like to think of programs, whereas in cryptography, for instance, in secure computation, you need to execute circuits. So the compiler actually compiles these programs into small circuits and our backend executes them. And we intend to provide common security guarantees, but the type system is relatively formalized. You can find more information about the framework at oblivion.com. So, moving on to solutions, there's a slight difference in the way we have numbered this. When we say task 1A and 1B, we actually mean task 2.1, which is really participation in the multi-party computation aspect. So, the task requires us to compute the minor variable frequencies. Here you have two parties, Alice and Bob, and each of them have a list of LAs. And over here, what we first do is that each party, since they have some part of the list, they compute the frequency of the LAs by themselves locally, and this can be done in clear text because they have all the information that's required to perform this computation. And for instance, in this case, Alice says the frequency of A that she has is 5 and the frequency of C is 1. And similarly for Bob. And once you have this, all that remains is to add up the frequencies of A and frequencies of C and compute the minimum amongst the two of them. And since this involves two parties, we need to use secure computation. In this slide and in the rest of the slides, whenever you see something in green, it means that we can compute this in lower text because it refers just to one party. And whenever you see something in red, it means that a second party computation is being performed. So this is the simple code that a user will have to write when he's developing something on BDF. Over here, all variables, you can think of them as in secret, except for if you specify, for instance, the number of test cases n over here is a public variable, and hence you specify it as public. And things like int at n, where what this represents is the size of the integer bit. So in general, when you think of it in clear text, we have 4 byte integers, but in secure computation, it matters as to what the size of the integer is. And we can specify that with parameters such as int at n. Moving on to task B, over here we need to compute the chi-square test statistic, and over here we are given, instead of one list, we are given a case group and a control group, and as suggested on the problem website, we need to compute the LL count or the LL frequencies of A and C for each of these. And this is actually exactly similar to what you did for task A. And in addition to this, we need to compute the chi-square test statistic, which is given by this formula. And since this formula involves a division, it involves the result may be a floating point number, and we need floating point computation and secure computation to do this. And when we have floating point computation, the precision of the number of bits used in the floating point computation can actually change the accuracy. So with that implementation, you can specify the number of bits required for precision, and when you specify the different bits, if you want higher precision, the amount of computation is higher, but you get a higher accuracy. For instance, you get accuracy of around 10 to the minus 8 when you have around 14,000 gates. And again, this is the code. I'm not going to go into the details of the code, but you can just specify variables, and all you need to do is you need to say, I have a float variable, and the backend does everything for you. So before I move on to task 2, let me just explain a building block which is secure set union. I think reduction of spanning distance and edit distance to secure set union is something similar to what the MIT Stanford group did and the UC group did. So let's explain how we do secure set union. Suppose Alice and Bob have two sets, and that's an example, and we want to compute the cardinality of the union of the two sets. In this case, the cardinality is 5 because the element is common. So the naive solution to achieve this would be to just sort the combined array. And I'm thinking of, so in this function, I'm thinking of the set as a list instead of a set, and I'm saying I can sort it. The reason you would want to sort them is because you want consecutive element, you want the same element to be close together so that you can remove duplicates. And once you have sorted them in a single pass, you can eliminate all duplicates and compute the cardinality. This is an n-log squared n solution because the practical sorting scheme, obvious sorting scheme that you can use is Bitomic sort. Although there exist theoretical sorting schemes like AKA sorting networks, they are not practical. So the question is, can you do better than n-log squared n? Turns out we can, and the reason is that parties A and B initially have half of the lists. So the initial half of the list can be sorted by each of the parties locally. And once both of them have these sorted lists, what they can just do is perform a merge, an oblivious merge. And once you have an oblivious merge list, you just compute the cardinality in a single pass. And with this, the complexity of this performing this merge is order n log n. We just use the merge that we use for Bitomic sorting. Now again, once we had this solution, we thought, we have n log n, but can we do any better than this? We have another solution. Okay, before I move on to the next solution, the code for oblivious merge. Again, in our language, we can just define recursive functions so long as the depth of the recursive function is bounded. So this is all for the ease of the programmer, and we ensure security for you. Yeah, so when we had this end-to-end solution, we thought, can we do better? And then we thought of a Bloom filter, and we said, perhaps we can have an order n solution. So in general, a Bloom filter is used to check for the existence of elements. For instance, so initially in a Bloom filter, you have an array of bits, all set to 0. Whenever you want to insert an element in the Bloom filter, you just hash it using iHash functions and set the appropriate bits to 1. For instance, say I'm inserting x, I set appropriate bits over there to 1. And similarly, after I insert all elements, if I have to look up if some element exists, all I have to do is I have to compute the same hash functions and see if all the corresponding bits are 1. If they are, with very high probability, I can say that that element existed in the original set. But what we are using the Bloom filter for is to actually approximate the cardinality of the set, and we can get the approximate size of the number of elements inserted in the set by using this formula. All this depends on this k, which is the number of hash functions, X, the number of bits set in the bit string used for blue filter, and it depends on the number of bits in the blue filter that was originally used. And once we have this, what each of the two parties do is that they compute blue filters locally for the sets they have. And once you have these blue filters, all you need to do is perform bitwise OR, and that would perform a set union operation on the two sets. And then you need to count the number of ones so that you can apply that formula and compute the estimated size of the set in clear text. Intuitively, why this can work in order n is because a blue filter represents some kind of concise information about the set. And the actual accuracy depends on the original, depends on the number of hash functions and the size of the blue filter that you actually take into consideration. The detailed parameters for what accuracy you would get and based on what parameters you choose is actually there in our detailed report, which is also available on beacon.com. So now that we have discussed this, let us move on to explaining how Hamming distance and end distance can be reduced to a set union. For performing a set union, you can use any of the solutions that we suggested. So the first problem for Hamming distance, Alice and Bob have input records of the type ref, SV type, and alternating sequence. What this meant is that you're given all the positions that differ from the original reference that you have. And for each record of type SNP or substitution, you need to find out which of the two records, which record differs from the reference, and if for both parties, if the same record differs, you want to count it towards Hamming distance only if they differ in different ways. To give you a simple example, let's say Alice and Bob have the following two records, and I'm taking a toy example just to explain how we compute Hamming distance. Say Alice has a record of the type, say, was at position 1, the odd sequence is T, and the type of the record is SNP. And similarly, Bob has a same record saying at position 1, the odd sequence is T, and record is SNP. We do not want this record to be counted towards Hamming distance because although they have been modified by both parties, they have been modified in the same way. But for say another record that Alice has, which is of the form at position 75, the odd sequence is G, and the record type is SNP, it is not modified by Bob, and that is why we want it to be a part of our Hamming distance. So in general, we need all the positions that have been modified, but not modified to the same value. So as was described by the MIT and Stanford group, the Hamming distance can simply be represented as a difference of set union and set intersection. Note that computing set intersection is same as the computing the set union because you can always say set intersection is SA plus SB minus SA union SB, and with that you can compute the Hamming distance. Moving on to edit distance, over here again the input records are the same. The only difference, and with SNP and substitution records, again, everything is the same as Hamming distance. But if, in case of insertion or deletion, if one party modifies the position, we need to add the length of the alternating sequence to edit distance. And if both parties modify a given position, we need to add the maximum length of the alternating sequence to the edit distance. Again, we decompose this problem as two different set intersection problems. Suppose in this example, I added one more record from the previous example. It says at position 10, Alice says I'm going to insert PCG, and Bob says at position 10, I'm going to add insert CA. And over here to edit distance, we need to, as per the problem statement, we need to consider TCG as a part of the edit distance as well. So Alice computes two sets. The first set comprises of all the positions that have been modified, And for the insertion record, we actually expand the position as 3 different records, and this is because it actually evaluates to add the length of the alternating sequence, which is 3 over here. And iDASH also computes another set which actually contains the data, and you need this because if Alice and Bob modify the same set in the same way, you do not want it to count towards their distance. And similarly, Bob computes the same set, and again you just express it as 2 different set intersection problems and get their difference. So this is all we have for our solutions. This is a graph which represents some other problems that we solved using of the EM and the speed up that we achieved in comparison to the state of the art in 2012. And you can find more details in the Oblivion.com. And yeah, we had a great time actually participating in this competition, and we are very excited to actually participate again next year, and we hope to see more bigger challenges, something that involves big data and so on and so forth. Thank you.
Thank you. Questions, please.
So when you say that there's no algorithms that run analog and time are not practical, what exactly, or what kind of algorithms do you need?
Sorry, I'm not getting it.
So when you say that only the sorting algorithms that run in analog and time are not practical.
AKS sorting network.
What?
The AKS sorting network?
Okay.
That
Because
is
they're
it.
learning more recent, like Wudersh's or Wudersh's algorithms.
The randomized shell sort?
What?
Are you talking about the randomized shell sort?
Yeah, the constant very small.
Oh, I see. I think I'll have to look into that.
Yeah, because you know, for us, we're not using it because the raw complexity is high, but for our workers, it doesn't matter. So
I see.
it's actually a good alternative. I
Okay.
mean, I understand that this saying if you can pre-sort, then merge sort is probably better. But if you don't have the ability to pre-sort 2 different sets, then we should say it's going to be more of a person sort.
Okay, I think I'll definitely look into that. Thank you.
Okay, any other questions? Okay, if there's no question, let's go in. Okay, our next speaker in this section is Sandy Zahu from University of Virginia. Sandy represents reading team for the past number 2 administrators.
Thanks. So yeah, one of the perks being last speaker here is that everyone has pretty much already seen so many years that I want to talk about. So as far as solutions go, I have a community here. So I'll be talking mostly about the framework and not solutions. As far as solutions go, we did the handling distance. We did not have a solution, or we did not have anything for data distance, but it's the same thing. We have this, we do settings, we use the settings section. One for the locations, one for the locations and data, and then we do the union. And finally, we also have another entry to the iceberg. So yeah, that's my framework. It's called C. It's built on top of C, small extension C. We'll talk about it a little bit. But the hope is existing programs can easily learn this language and use it wherever they want. We don't have too much of a learning curve. So yeah, this is sort of the run from statistics from the sample run. So the small samples are provided. We don't actually have, I saw the numbers for the actual ones, but I didn't have to publish order. So we were really excited about getting one, sort of the execution speed up to over 2 million gates per second. That was, so I really wanted to put that up there. So to give you an idea of, should I see, or whatever. To give you an idea of what it looks like code in our framework, this is the code for batches merge. This is the same merge sort that the previous speaker was talking about. To do the merge, see, this is normal C code. There's absolutely nothing special going on here. In fact, you can just run it through GCC and link it, because there is no extra keyword that comes out of GCC. The only thing that needs to be coded specially in order for this to work is the comparator that you see there, right? So all you need to do is find a comparator that does compare three integers and solves them if necessary. And that will look something like this. There it's essentially two kinds of variables in an element, normal variables and ones that are executed correctly. That's all. So you write the extra keyword of it for the variables that need to remain secret and of it for any if conditions that depend on such conditions. Now, one of the things that will obviously, because it's built on top of C, and it's just simple detriggering that is applied on OC before it gets passed on GCC. So, first of all, our programs are compiled to binary before they run. It's part of why we execute this rule that we can get. And the other thing is that the existing C library is all available as is out of the box. So, one question that somebody has is, okay, if we already have an existing C library, why do we need another sorting function? So if you look carefully, this is the header for the normal key sort that's already communicated yesterday. You can't really use this because the comparator requires int to be a return value. If you compare it to secret values that nobody knows about, the result of comparison cannot be a normal int. Come out with a claim if you try to use this, right? So that's generally what programming this language looks like. And like I was talking about, we get all the previous libraries out of the lots. So file.io, key threads if you want to do multi-threaded stuff and whatnot. Look, we are researchers at the end of the day, and you're really bad at maintaining software for the long run. So we want to get out of the way when it comes to making usable, making large extended libraries, system libraries. So if there is an existing library that you really want to use, if you have already a code set up to parse these CF files and whatnot, you should have to rewrite it in our own language. You don't have to wait for us to implement all these extra libraries and whatnot. So these are made it easy to use whatever's already out there. And to give you just the details of the cryptographic scheme that we use, it's 8-bit secret labels, CL circuits, using AES headers to take advantage of AES instructions. And we already have an experimental set intersection implementation, private set intersection implementation based on the element, which is known to require much less bandwidth and whatnot. We also use the half-base scheme. Half-base scheme that was that's due to appear in Eurocrypt, and it is designed to reduce bandwidth usage for EL server circuits. So in normal EL server circuits previously with ESRs, every nonlinear gate needed 3 ciphertexts to be transmitted. We figured out a way to do it in just 2 ciphertexts and reducing the bandwidth usage of EL by 30%. So we use that. That helps. So again, other than that, it's open source, available for use. I realize that some of the problems that we solve here are simplified so that we can tackle it much more easily. So if somebody wants to use it for more realistic purposes, and they want to tell us what's more interesting in our field, I'd be very happy to talk to you. Please get back to me and just play around with it.
Thank you, Sami.
Questions?
I've seen in previous implementations of parallel circuits, big problem generating keys. Just there's not that randomness on cloud systems. So do you have any problem generating keys or?
Keys meaning like OTPs or labels?
Yes, yes.
In our case, all we do is that we have a private, some entropy we gather from /get/random, and then we just use it to see the random AES and whatnot, running counter mode. Yeah.
So combining any kind of security protocol in a network and threaded environment is really great. How do you ensure that the developer doesn't shoot themselves in the foot by running many things in parallel or doing something strange on the network?
Yeah, that's a really common question. So there is no general answer for this. In general, we don't. It's just like any other program being written in C, there are always possibilities of vulnerabilities. Just like the SSL, it's been used forever, and we still find vulnerabilities and whatnot. We just sort of making it easier to do what people are doing right now. That's all I'd say.
All right, then the question is as a speaker, and then we have 5 minutes.
Maybe we can speak.
We will sleep. We go to the next section, section 3. Let's welcome the next speaker, Dr. Yuzhe Tang from Taiwan University. Sorry about that. Yeah, we are running late.
Okay, hello everyone. My name is Yuzhe Tang. I'm from Syracuse University. So I'm a junior faculty member over there. So in this competition, our team consists of 4 people. And we have Scott, who is a PhD student of mine, and he is more responsible on the GWAS competition part, task 2.1. And for the task 2.2, we have 2 master students. So I will give a brief introduction of the task itself. Actually, this is pretty much covered by previous presenters. So for first computation task, we are doing statistical analysis for GWAS, genome-wide associations study. Basically, the goal is to find out the association between a disease and a human genetic feature. So by composing the computation, we have two specific computations. One is minor alien frequency, the other is X well. So just to give you a sense what MAF is. So if we have 5 individuals here, and each individual is associated with this snaps, then basically we need to count the number of areas. And here we have 2 areas, and we need to output the frequency of the minor area, which is 0.4 here. And the other one is basically a standard statistical analysis. So in terms of the algorithmic model, this is essentially can be boiled down to a counting problem. For the second one is about comparison, added distance and approximate added distance and happy distance. So from algorithmic perspective, this is really a set operation, a merge operation followed by counting differences between 2 factors. So in this presentation, let me focus on what we did with this programming framework from the University of Virginia. It's called the PCA, the Particle Circuit Framework. Basically, it exposes a C-like programming language interface, and with some restrictions. And after that, it has a compiler, which is called the LCCR. And so when you run the program, it also provides an interpreter or runtime system for BATYARD. BATYARD is based on this garbage circuit or previous transfer. We also initially we tried another protocol, GMW, but GMW is more like a runtime system. It exposes a very low level programming language interface, which is circuit based, and it makes it very difficult to program because every time you have to write a circuit manually by yourself. So after that, we decided to choose this one because it provides high level programming language. It's really simple. It's both a C kind of programming language interface. We just write those counting problem and also the added distance problem using C program. It's nothing new. But the point here is there is restrictions for those C kind of language. And what we did in this task is essentially to get rid of those restrictions or work around those restrictions. So, first restriction is inflexible control flow for data access. So basically, in a C program language, you have break, you have generic loops, but in those kind of language, there is no break, or there is no. So when you write a loop, you have to specify the number of iterations to be multi-time constant, and so that kind of present a challenge for us to implement our algorithm in an efficient way. Also, for array access, it essentially works into an open operation, and is the number of elements in the array. So if we want to implement this merge algorithm, then it's very hard for us to implement that. So we end up with a solution which is not optimal. So we end up with ON algorithm. And the way we do it is for each element we just scan the other list, the entire list on the other party. And by using this strategy, we can actually input something in the PCA programming language. If we use a merge sort, which we have tried, then we will run into a problem which basically the control flow of the program will be very much dependent on the sensitive input data, which is something this framework prevents. The second restriction is more like the size of the input data. Battery now and also the signature in the PCA program, it has some kind of limits, which limits the size of the input to less than just 8,000 bits. And by this restriction, it's very difficult for us to handle the big data inputs, or even for the sample data inputs. So the way we work around this restriction is to kind of partition the data into multiple small pieces, so that each piece can fit into this restriction. It's very easy to do that for the first task, the GWAS task, because essentially there is no correlation between different lines of the inputs or the genotypes. They are independent to each other, so you can just partition them and do the computation between for each partition. But it's very difficult to do that for the second task, which is adding distance or handling distance. So in the end, the way we deal with it is we partition based on some kind of feature in the input data, which is the concatenation of prong number and the position. And the interesting thing there is although there are some correlation between different genotypes, but there are no correlation between the combination of these two numbers. The last one is more like because of the framework does not support negative numbers and floating point computations. So we come up with a very high level workaround solution to do that. So for example, if we want to calculate the division of x and y, which are both integers, and the output should be a floating point number. So the way we do it is we just right shift. Locally at each party. So by doing this optimization, we can have around 5 to 9 times speed up. And the other thing is, if you kind of domain-specific optimization for input data encoding. So, for example, here we have 4 numbers, right? Usually, how many bits do you need to encode 4 numbers? 2 bits, right? So we end up with just 1 bit, and this is specific to the input because for each line or each genotype, we observe that there is either basically 2 of this will co-appear, but it will not, for each genotype, it will not have more than 3 possibilities. And we are, actually, it's not a done deal, we are still working on to improve this merge operation from just to get rid of this complexity. At the system level, we did something with multi-threading or multi-processing. Basically, we run the program in parallel with multiple processes, and we so because we have to partition the input into multiple pieces, usually it's more like 100 pieces. And if we run it with 100 processes, then there will be some it will slow down the performance if we have only like 4 cores. So the way we work on this is at a specific point in time, we only allow processing of 8 processes. So only when those 4 processes finish, we start another 4 processes. So by doing things this way, we can avoid this bottlenecks now. In terms of security guarantee, it is pretty much provided by the underlying BACTEA or PCA framework. And this framework can provide different security against the different adversary models, from semi-honest to malicious models. The optimization we did with this project actually leaks some information. The input size is leaked. For example, number of lines with from value 1, this number is leaked. But in our design, we think that this is more like a statistical or aggregated information. So maybe it's better than disclosing the at the level. So in terms of system architecture, it works like this. Basically, we implement a code generator, which takes inputs from the kind of templates we wrote for each task, and we take the inputs, the private inputs. So as I mentioned before, we leave this input size data and that information. So before we put the input into the PCA program or framework itself, we did some pre-analysis to see how many lines in this input regarding specific attribute values. And then use those values, we can generate more than 1 C programs. And we feed those C programs into the underlying PCA platform. And this inside the code generator, for every distance task, we have to generate dynamically the length of the loop. Remember, in previous slides I mentioned the number of iterations in a PCA program has to become outline constant. So that's why we have to do this dynamic, kind of dynamic generation to generate this number of iterations in the loop. For GWAS, we use this code generator to do the data function. Okay, so we have some performance results. We did performance study in a network setting. Basically, we test with 3 typical setups. One is local, the other is LAN, the third is internet. Local means we put Alice and Bob onto one machine. So basically, they share memory resources and CPU resources. LAN means we have 2 machines, and those 2 machines are with homogeneous hardware setup. They are interconnected through a local network, local area network. And the third one is basically it's based on the setup provided by the organizer. We use 2 machines. One is in UCSD, and the other is in Indiana University of Groningen. And we did this 2 tests. So this is actually outdated data. I will show more recent results soon. But just to give you a sense, this trend is still the same. When you put things onto just one machine, actually this takes more time than if you put things on multiple machines, if those 2 machines are not far away from each other too much. So the reason is that I think so. Our suspicion is is that those kind of computation is more like CPU or memory intensive. If we put them on one machine, then the contention will become the bottleneck. If we put them into two machines, but they are not far away from each other, so that the communication channel will not become the bottleneck, then to optimize the performance. But if we put it to the internet, separated by far away, but then the performance will have some degradation. But you can see, anyway, so you can see the numbers of internet is actually better than putting things together. Okay, so we also tested the performance against the data sizes. This is for land sample. The last thing I want to mention is when we submit the solution, and then we pick out some optimizations, and now we have this optimization. So with this optimization, basically we do some local computation. We can improve the performance by speed up from 5 times to around 10 times. So whatever you see increase size, divide them by 10 times. Okay, so yeah, thank you for your attention. Any questions?
What is the optimization?
Okay, so I basically did various kinds of optimizations at different kind of levels. In the computation, it's very hard to start. So in the computation level, as I mentioned, if we put, because the MPC is the bottleneck of the system, if we can do the local computation as much as possible, then we can minimize the computation that needs to be done by MPC, right? So that's one optimization we are doing. The other one is, as I mentioned, so if you use for these four numbers, four possibilities, if you use 2 bits, then it could increase the size, input size to MPC program. So we observe this kind of domain-specific feature of input data, and we just use 1 bit. This actually increases a lot of performance.
Yeah, so you mentioned this merge sort approach may give some information. Can you elaborate a little bit more? So you mentioned your N-square scheme is better than the merge sort.
No. So this routing will not leak the information, but the normal merge sort will leak the information.
Yeah, what's that kind of information?
So based on our experience, we first implement this merge operation, right? We implement this merge operation, and the framework itself throws an exception, it crashes. And our suspicion is that we think when you implement the merge operation, basically you have 2 pointers at each of these 2 lists. And the movement of these 2 operations is dependent on your input data. And that kind of dependency creates some kind of leakage of the algorithm. So later on, what we did is we very naive approach for one input to just scan the other list, entire list. This gives us like a suboptimal solution, but it works. That's the most important thing. And later on, so that's what I mentioned. We're still working on improving that one.
Thank you. Dr. Yi Hoffman from the University of Notre Dame.
Hello everyone, my name is Yi Huang and I'm team from University of Notre Dame. So this competition basically challenged like two tests. One is secure distributed competition, and the other one is secure comparison between genomic data and specifically focus on algorithm competition. So in our case, we use the secure sharing technique. So the main idea of the secure sharing technique is that the secret is shared out of like n different parties. We call like T or more than T parties get together to the secret. And there are some other features of the secret sharing scheme. For example, like if you're trying to perform the linear combination of the secrets, this operation can be done locally. But if you're trying to perform the multiplication of two secrets, it involves like one round of interaction, like the linear combination. And also, if you're trying to evaluate the performance of crosscode that uses secret sharing, in other words, like two different performance metrics. One is the number of interactive operations, is the number of multiplications using the crosscode, and the other one is the number of sequential interactions, which is called rounds. And in our talk, we use like the square bracket X to represent share of the secret X. And these are the four building blocks that we use in our solutions. And the first one is the marks, X and Y. So it takes like two shares of secret, X and Y, and it returns the share of their product, which is C. And it takes like one round and one direct operation. And the next two building blocks is the comparison inequality. And it takes like two shares of secrets, which is X and Y, and it also takes their size, K, and then it returns the secret bit, which is B, which has value 0 and 1. So depending on whether those two shares are the same or not for the equality, it returns 1 or 0. And the last building block is the integer division. So it takes like shares of two secrets, X and Y, and it also takes like the size of K, and it returns like Z, which is the quotient of like this division protocol. So this integer division protocol, we use the Gaussian method, and this requires the normalization of X and Y, and it takes the following graph and the direct operations. Okay, so let's talk about like how we deal with like each task. So the first task is the minor linear frequency. So the idea is that each input party, they locally count the frequency of each nucleoside in case and control files. And then they secretly share that frequency to two other computational parties. So after the distribution of shares, each party will have like 8 different frequencies, and they are like secretly shared. So it's like 8, and then each party they aggregate like 4, and because like there's no difference between the case and control group in the minor linear frequency, so each party they aggregate 4 frequencies corresponding to each nucleoside. So after aggregation, we have like 2 frequencies, A and T, that represent frequency of nucleoside in both of the case and control files from 2 parties. And then we call the less than building block on these 2 aggregate frequencies, A and T, and then you get the secret binary value as a result of this operation. And then we perform the linear combination of like B, A, and T to get the secret shared version of the frequency. So if like the A is less than T, the result is like 1. So you choose the frequency of A out of N T and vice versa. So after we get the share of like this frequency, these three parts get together to reconstruct the frequency. And the chi-square, the statistics, is also pretty straightforward. So the way that now we need to combine the frequency pairwise instead of like the combined forward. So for the if like A, B, and C and D represent those four frequencies that we aggregate together, and then use like the following formula to compute the chi-square test. And it goes like A plus B plus D, and A plus B and C plus D are like output information, and we only need to perform the compute the following computation, which is AD minus BC squared divided by B plus D and A plus C. And it involves like the multiplication and each division product. And our solution can achieve like quantitative accuracy using the formula. Okay, the next part we're going to talk about the Hamming distance computation and talk about how we deal with this problem. So the main idea of like this Hamming distance computation is that each input party given the data set, they divide the data set into two different parts. And then which is called substitution group and then SNP group. And then they get together and perform the Hamming distance between a pair of SNP group and then a pair of subgroup independently. And then they add them together to get one Hamming distance. And finally, they compensate some offset that is introduced by this separation approach. So the first part of the solution is called extraction. So basically trying to extract all the necessary information from the input file. So the first information we need to extract is the default position. So basically extract the chromosome ID and then pass from the input file, and then using the following formulas to compute the position value. So here 2.5 times 10 to 8 is the maximum length of any chromosome that exists. So by using this formula, we can guarantee that if we record a different value for either chromosome ID and pulse, we can get like different values of position. And next two fields that will be extracted from the input file is the reference and optimal field. And we find that like for these two fields, the length of their values depend on the type of the report. Depends on whether the report is like type of substitution or the report is type of SNP. And we found that for the report that is type of substitution, it's maximum length of 100. So we basically use like 200 because of each character we represent by 2 bit values. So we totally use like 200 bits to represent the value of these two fields, and we further append its actual length, which is 7 bits XN. So basically 207 bits represent values of these two fields for the sub-report. And for the SNP, because like it's only like one character, so we use like 2 characters, a 2 bit value to represent these two fields for the SNP report. And this also explains the reason why we separate the entire data into 2 parts. That because like solution you record the building blocks of comparison equality on the values of the reference alternate. And the cost of running those building blocks actually depends on the size of the values. So in other words, like if you want to perform the comparison equality on the 270 value, its cost is way more expensive than running those building blocks on 2-bit value. So you want to make sure you perform those expensive operations only on the necessary amount of the data instead of all of them. And the second part of extraction is that, as I mentioned earlier, we divide the entire data set into 2 different groups, and the subgroup consists of all the reports that is type substitution. And then the SNP group contains like both of the SNP and the sub-reports. So the reason why we include the sub-reports into the SNP groups that it's not use them to compute Hamming distance, but rather you want to use them to compensate offset that is introduced by the separation approach. So, for example, like the values of alternate reference field for the SNP record is chosen from 0 to 3, but for the sub-report in the SNP group, if we find the length of those spheres is greater than 1, you use like new value 4 to represent their values. So here it's not with actual, their actual values of the reference component, but with new value 4, because like we only use that information to compensate offset, but not like the computing time distance for those values. And also like we tag like the recursive snip and stop type differently. So for example, I use like tag 0 to represent this is the recursive snip type, and using 0 to represent the sub-record, the snip group. So after extracting those three fields from each file, so each input party, they basically sort every record in those groups locally, based on their condition values. And then we pack the down records into each of the snip and substitution group to make sure the proportion, which is like 30% and 100%, which is the maximum proportion that could appear in the genome data set. And this is information we get from the organizers. And for the position values of those boundary records, we set to be like maximum average position, maximum average position constant to make sure there's no overlap between the positions of boundary record and the real record. And the last part of the instruction is that after we have like those two, after each input part has produced the two groups, which is the snip and subgroup, input part 1 basically multiplies the position value of every record in those groups by 4. And then part 2 multiplies the every position value of each record by 4 and plus 1. And the reason why it's doing that is that in our solution, we might add in some dummy records into the data set. And then for those dummy records, their position will be the same to some of the existing records. So given the two records that have the same positions, we can't quite tell whether there are two real records, or like whether one is real, one is dummy, or both of them are dummy. And by doing one transformation, you can guarantee that if originally they have the same position, now their position is different by 1. And originally they have different value to their positions, now their difference is greater than 1. And now if you find they have the same values of positions, we knew that they are dummy records, and then it's not which benefit to the time distance. So after we extract information from the file in the rough manner, each input part basically shares the values of 4 fields, which is position, reference coordinate, and tags. And then they send the shard of those information to other parties. And now they can start performing computations. So at this point, each part has like 4 different groups, and 2 snip groups and 2 subgroups, and they are from the 2 input parties. And then before they start computation, they want to first perform the obvious merge between pair of snip group and then a pair of substitution groups based on their prediction values. So the result of this obvious merge is that you have like one sorted snip group and one sorted substitution group at the end. And then you try to perform Hamilton computation between a pair of snip group and a pair of substitution group, and then try to back them together. So to perform the obvious merge, we use the Pythonic, the sort of merge network. And then the way it works is that if you're trying to merge n different records, it requires long n rounds. And then each round it takes like n compare and exchange operations. But the problem of this Pythonic search network is that it only works when n is power 2. But in our case, we can't guarantee that feature. So the way we meet this problem is that in each round, we only add some dummy records, but we only add it when it's necessary. So I think this is one approach. And another approach is that we can have like dummy records at the beginning of the first round to make sure the total amount is like the power 2. But the problem of this approach is that now we have to start with like a large amount of now you have to perform like the larger amount of comparative exchange operation in each round. But if you use the first approach, you can perform a smaller amount of comparative exchange operations in the early phase of rounds. And for those like the value of position of the W recourse is set to be identical to some of the existing recourse to satisfy Python property. So after you perform the abuse merge, you have like two sorted groups. One is the sorted SFP group, and the other one is sorted the substitution group. And then for each group, for each pair of the consecutive recourse, we basically obvious the following four values. And the first one is to compare whether their conditions are equal or not. And the second one is whether their conditions differ by one or not. And the next two is like whether those fields are equal or not. So it's like AI, BI, CI, represent those four values. And then the timing distance for each pair of the groups can be configured using the following formula. So we initialize timing distance to 1, and then for each pair of consecutive groups, to determine whether if you contribute 1 to the timing distance or not, we first want to make sure like their conditions are different. So the result of 1 minus AI should be 1. And then if their conditions are different, we further check whether their difference is greater than 1 or not. So if their difference is greater than 1, it means like originally their conditions are different. And then but if their conditions are same, if their conditions are different by 1, which means like originally their conditions are same. And then we further check whether the values of the reference fields are equal or not. If it's equal, we further check whether the values of the alternate field is the same or not. So all these operations will be performed in batch, which means like it's not performed in a sequential manner, but rather put together and then perform competition like in one round. And there are some other parts that we haven't talked about in this talk. And the first one is that, as mentioned earlier, like we divide the entire record into two parts. But the problem with classifying separation is that there might be two records that have the same conditions, but their types could be different. But using the solution proposed in this talk, we can't actually pinpoint that part. So we need to have like another mechanism to compensate that offset. And the second part is that because like for the time-based computations that are performed in the split group and the substitution group, we use like different module sizes for the computation in those groups. So at the end, if you want to get one final Hamming distance, you need to perform the shared conversion from the Hamming distance of one prime module size to another, so that you can actually perform the arithmetic operation, with addition of the two Hamming distance values. And finally, we also like need to find the optimal match size that runs the fastest in the advanced setup, and also want to make sure like it should not exceed the memory upper bound of virtual machine through the execution. So we are not trying to minimize the memory requirement, but rather we are trying to fully utilize the memory that we provided. At the same time, we are trying to minimize the runtime of this test. So again, that's our talk today.
Any questions?
When you were talking about the precision, what do you mean?
So like the result of division is like just like it will be correct up to 10 to the minus 6. So that's the 20 is like the accuracy I'm talking.
Well, this will get better precision if you use larger heights, larger frequency.
Yes, so I mean you can get like whatever accuracy you want, but the performance will be slightly different depending on what accuracy you're trying to get. So you can use like provide different parameter size for the integer division. It takes like the value of k, which is size of the values, and if you provide and you can modify that to get the better accuracy.
You also need to make sure that you don't overflow too much, because the more data you have to calculate, sometimes you may overflow. So how do you pre-calculate the size of the types you use based on how much data you can deal with going to be in the challenge?
Right, so you basically use the sum of the upper bound, for example, like how many SNPs in both of the case control fires, and then you use that information to basically decide what's the model size you want to use in our protocol.
You don't do this dynamically, you do this before.
Yes, based on the maximum size, it shows the values.
Okay, and the batch size, we tried to do this automatically once, but we didn't get to good quality. Can you do this automatically? Decide batch size automatically at runtime?
Actually, we didn't. We actually tried different batch sizes in the best setup and then choose one that gives us best performance.
And we do this. Thank you for the presentation, and let's welcome the presenter, Nathan from the Sacramento. Hello, I'm Dan. I'm not using the microphone. I'm representing a larger team, the SharePoint development team in Cybernetica. This particular competition entry was built with the help of Nagal and iDASH. And I'm focusing on a slightly different topic here because our entry to the competition was slightly different from what was expected. What was expected was either fully homomorphic encryption or just homomorphic encryption or two-party secure computing, and we're currently most efficient in three-party computing. Then I wanted to put my presentation slightly in a different view, but I will also talk about our entry. So first of all, the SharePoint secure computing model as of today. This is, first what you have is you have input parts, there are one on the left, input parts. You can have any number of those. These can be mobile devices, web servers, whatever you like. Then there are computing parts. These are the folks you can call cloud servers. We currently use 3 because it's the most efficient set of protocols we have. You can use almost any number larger than 1. And then once you have done your computations, you give your work result parts. So it was already explained in some talks that the idea is that if you have a database, if you have any secret value you want to protect, and you use secret sharing on it to distribute it among the computing parts. And what you get is that each computing party has a piece of each secret, and that piece is random enough to be considered equivalent to encryption. The nice thing with multi-party computation is that it can calculate with the results without reconstructing the inputs. And the nice thing is you don't really always have to do circuits. I know it was claimed here that multi-party computation is mostly about circuits. It's not. You can also do programs in multi-party computation. But it depends on the kind of protocols you use. Once your computing parties have performed the computation, they will publish the results to any result parties requesting these results. So that's a generic model. With one computing party, this could be a fully homomorphic encryption. With 2, you could do carded circuits among the computing parties. So it's not really limited to the kind of approach to use. It's generic enough. Currently, this is how we're working. Secret sharing, very simplified. It's really, if you have never heard about the concept before, you take a secret value and you find some numbers, but some objects are secret value. And in practice, we do this in modular cyclic rings or fields, but for this explanation right here, it's just 2-digit numbers. So modular 100. But this is in practice what we do again, we choose a rather large field or ring. In ShareMine, we use hardware types, meaning we use rings size of 2 to the power 32 elements, 4, and so on. And once you have secret shared your data among the computing parties, then what you do is you can have these primitive operations that are composable. So you have your secret shared inputs, and then you start an instruction on these. And what you get is you get secret shared outputs. And the key here is this is like microcode in a CPU. You can say add, you can say multiply, and then you can say add or multiply again. So it's nice, it's fully composable, it's nicely programmable. Most today's MPC-based secret sharing has universal composability proofs, meaning that you can run these operations in sequence, in parallel, without any privacy loss. So the strengths and weaknesses of this approach. Well, the strength is that it's easy to write code for. You take an application, or you take an algorithm on Wikipedia, you put it down in the programming language you use, you apply some privacy patterns, and you use pretty much try to reuse classical algorithms. The hybrid execution model again allows you to balance public code with private code, also on that computing parties. We don't force everything to be private at computing parties. This is sometimes this has been an issue with carbon circuit implementations, but recent ones are also flexible there. This is a very, very well performing set of protocols, especially for arithmetic circuits, and well, also for string data, depending on if you're using the right secret sharing scheme. You don't always have to use the linear arithmetic one, you can also do bitwise secret sharing, like Galois fields. But I mean, very high performance. This can be with decent optimizations and high parallelism. It can be about a couple of orders of magnitude faster than carbon circuits, depending on the task you can handle. And the storage overhead is rather small. If you have 3 servers, then each server goes exactly the same amount of data that you would if you just put the data together. So secret sharing doesn't increase the size of the database. It just makes sure that it's distributed in random pieces among a set of servers. The weaknesses are that the best possible protocols we know of with the best efficiency require 3 servers. You can get efficient protocols with 2 to n servers, especially if you allow pre-computation. But 3 seems to be really nice, and if you're with 3, you also get information theory security, meaning that it's basically one-time pass. You can let multiple computers come at you. You just have to find new communication channels. The weakness is that performance profile is not immediately intuitive, but that's the trouble with almost any algorithm, any paradigm here. You need to optimize heavily for parallelism, and it really pays off. Sometimes silly optimizations really pay off. You just do a 100,000 multiplications at a time, and it takes as much time as 100 multiplications. So really can make a difference. In some cases, custom protocols perform better. But that's again the case with many protocols. And nowadays, I've also seen results saying that general secure multiplier computation for set intersection can be as fast or faster than custom protocols. So, genome data and MPC, there are several scenarios for the use. I would argue that secret sharing is very similar to homomorphic encryption, that you can store information for extended periods of time. It's not one-shot computations. You secret share information, and then you can reuse it for studies again and again and again. These particular figures from our bioinformatics paper, I'm not going to explain all of it, just to say that there are several scenarios we envisioned in that paper. One of them was like not more private version of 23andMe, where secure computation ensures that the privacy of donors is better ensured and there's joint control over it. And all kinds of international or inter-organizational consulting studies can also be made this way. So, developing an application for ShareMind right now is similar to some other frameworks. First, you have a data analysis task. You figure out your algorithms or business logic, and then you implement it in our C-like language, which is called secrecy. And if you provide it with the data model description formats you're using, then you get the package you will install on the application server. This is very much similar to your Java application servers or .NET application servers, where you implement something and then you deploy it there, and then the ShareMind application server, in this case, makes sure that this application that you written runs securely. However, you also want to integrate this computation with your standard applications, and for that you have the controller library, which is basically a client application library. You can use it to build mobile, web, or command line applications. It depends on what your user experience requirements are. And of course, data model needs to be shared. For example, in the competition here, we need to make sure that the information uploaded from the parser and uploaded from the file is in the same format as what will later be loaded from the database. So we also included a database in all our solutions, meaning that we don't have a one-shot architecture. We usually rarely do these one-shot architectures. We just upload data and immediately compute and immediately return. Typically, our approach is more, we collect data over a period of time because rarely several people are online at the same time. And then we just store it in the database and later we pull it up when all the data has been collected and calculated as needed. So our competition entries, a few details on those. I've got the cost numbers wrong, I see it now, sorry about that. It should be 2.1 and 2.2. So we implemented an importer and analyzer tool for both tasks. The importer parses the file and uploads the data to the ShareMind system. The importers were C++ programs on the client side, and the business logic that receives data and stores it in the database in secrecy. Both together are about 200 lines of code. A lot of that is database operations. Analyzer, which does the actual chi-square, is also mostly the client program also invokes the server and the secrecy script, compiles secrecy script there, and both of them together end are about 200 lines of code, most of them database operations. So our implementation actually did several passes to the ShareMind runtime. These operations we use for that task were secure integer arithmetic, signed, unsigned, floating point arithmetic, including division. So I heard that some other people are also using floating point arithmetic, which is very good, and I also heard that there's a lack of division operator for some paradigms. So that was probably, I think, for FHD, because with various flavors of MPC, division is doable on both integer and floating point arithmetic. And here we used arithmetically secret share types, meaning linear sharing using addition as the operation. For the having distance version, we pretty much wrote the same kind of structure, but the analyzer was about 100 lines longer on account of having to use different kinds of paths to making more decisions than with this chi-square test. For that, we use secure integer arithmetic shocking against secure AES. the AES was used to encrypt the secret shared strings and then just open them and perform some operations in the public. But because these operations were run on AES encrypted strings and not in leaked. And this helped us get past the merge situation, which we didn't have to do the n-squared approach there. This is a technique we're using a lot with different kinds of aggregation, merge operations. Recently, there's a paper on that I refer you to if you're interested in However, what I wanted to focus mostly on in our work is that we felt that implementing these algorithms is not something, even though the programming tools have reached an impressive level of maturity, you don't have to be a crypto PhD anymore to implement yourself. So what we decided was that we need to make this tool an extra abstraction level higher. And well, this is not what we shipped for the competition because the rules of the competition did not ask for this. We would have had to package it in a strange way. So for the competition, we just extracted the functionalities underneath and shipped those. But what we have built is we have taken the free R statistics tool and computing. So the syntax is pretty similar. There are a few things different, but we can make those look the same as well. And it works in the same model. It's, let's say, the remote data storage model. You can connect to the shared database. Let's say you share a data warehouse hosted on a ShareMine installation. And you can ask it to perform a variety of operations. And it will do it, and it will disclose some of the results to you if the policies allow to do that. So it also has some other privacy-aware functionalities, like making sure that when you're giving in some output to the user and you're not leaking too much. For example, on the left we have a standard plot from R, on the right we have a more conservative version from RMind, which gives you a density plot or like a heat map more than actual plot values. The right one obviously leaks significantly less. However, it also removes some of the outliers. You see on the left one, the public version of the plot has some outliers. You can clearly identify right one doesn't have those because they're not dense enough. So by now we have a rather impressive set of features on RMind. Everything here is running secure multiplier computing. We have almost most of the descriptive statistics. Quantiles are very nice. You can do 5-number summaries, very popular for data test and checking the data. You have the most popular frequency analytics tools. Quality assurance is something that statisticians ask for when you talk to them. They say that you have to see the data to make sure we understand what's in there. We try to convince them to use descriptive statistics instead. However, we have versions of filtering and outlier removal, which they can use to make sure that there are no random stuff in the database. With outlier removal, both on well, simple things just by manual thresholds, but also with mean and absolute deviations. So it's a popular method. We also support the full extract transform loads pipeline. We can sort, merge, and aggregate meaning SQL group by style queries. We implemented all the tests we could think of would be reasonably usable in genome operations and also other statistics. Paired and non-paired t-tests, chi-square with various number of attributes, operator armitage, transmission disequilibrium, Wilkerson, and weakening. Also, we thought of multiple testing, which you need if you're doing GWAS, because you have so many parallel tests, you need to make sure you check what's the statistical power of all of them. So we also implemented the Monferroni correction and Benjamini Hopper procedure to make sure you can check after these tests that your results make sense. Also, there's regressions, linear and logistic, and we're continuously implementing new functions currently when working on PCA. People have also mentioned legal situation. In Europe, the situation regarding data protection is a little bit tougher than the US. However, last January, the previous year, we got the local data protection agency to accept that secure multi-party computation, if run correctly, does not constitute processing of personal information, meaning that data protection legislation doesn't apply, meaning that we get our hands on a lot of education data for analysis. This January, we cleared another hurdle. The Tax and Customs Boards agreed that using this technology does not mean that tax secrecy is compromised, meaning that a week ago, we actually started running an application where we are linking currently 16 million tax records with about 500,000 education records, and then analyzing using the RMI tool to determine whether IT students who work during school fail more often. Also, contracts were mentioned. For if there are more than two parties, how do you make contracts? That really depends what the roles are. It's a nice challenge, but we also figured that one out. We also have this within the same project. The challenge is understanding again who are the input parties, who are the computing parties, and who are making the queries. And the contracts are slightly different based on that, but not too much. Also, if you're interested in a more thorough legal analysis of that technology, then there's a EU practice research project, and so rather recently published a 100-page legal analysis of these kinds of technologies. And if you want to read it, then the slides I think will be up later, and you can look at that. There are some papers that give a better understanding of what we do and what model. From a genome perspective, probably the best thing you should look at is our bioinformatics paper from 2013. We have improved performance of the system significantly by that time. There is also a meaty, fresh PhD thesis from last week that does about all the statistical analysis methodology. And these folks are paying for my 5,000 mile trip here. In order to get that money, I got to show you that. So.
Any questions? Yeah. So I have a bunch of questions. My grad students are watching it or asking me to ask you. All right. So number one, we're going to keep this small. I'll ask one to start. How easy is it to extend ShareMind applications to generic multi-party situations? Are any sub-protocols in ShareMind on to three-party cases only?
What is generic secure multi-party?
So like much more like a larger set of players in the system.
So what we're doing right now is we're developing
and more arbitrary computations than just the statistical computations.
Currently, if you want to do any computation, just ShareMind is a set of primitives. Our three-party protocol suite has about 550 protocols. So you have 550 primitive operations. These include signed integer arithmetic, unsigned integer arithmetic, floating point arithmetic, Boolean operations, string operations. Just combine them, compose them. There's an API, there's a SDK out. We just launched the open source SDK this January. It doesn't actually contain the crypto. We didn't think people want to wait. It contains an emulator that estimates the running time of the algorithm for you. So you run it on the emulator, and then when it tells you, hey, it's going to run for 2 days, we want to optimize that. And it also can give you a nice performance breakdown of where your bottlenecks are. It doesn't have a very Apple-like user interface yet, but we're working on it. So that's one thing. Second thing, we're designing new protocol suites. So the idea is that everything in ShareMind is designed so that you can just switch the underlying protocol layer. And as long as the secrecy programming layer is not affected, secrecy knows nothing about protocols, nothing about the number of parties. It just has security domains, meaning that, for example, this information is shared between UCSD, Indiana, and somebody else, and now I want to run this algorithm on this security domain, and Sherman should take care of that. We are implementing several two-party security domains as experimental ones. We have some that scale up based on Shamir secret sharing, for example. And I'm desperately waiting for somebody to help me implement one based on homomorphic encryption. So ideally, if we are successful, then you will just retarget your algorithm on a different security domain and run your algorithm on another set of protocols. That's what I'm working towards. I'm not fully there.
So you mentioned that your protocol can work with more than 3 parties. So how scalable is that? Like, do you do end-to-end communications?
We have lots of protocols first, so they're not very good. The main thing is we usually try to convince people to use the official version if they're in a hurry. If there is a distinct need for having 7 parties, for example, then it's not badly to pay for more communication. I can't give you exact costs, it really again depends on the operations you use. It gets more expensive the more parties you have, that should be obvious.
So when you make let's take additional questions offline and
there was one.
I just was wondering if you could quickly mention if you do anything for diversification. So clearly, if the 3 parties get infected by some malware and the same vulnerability, there's system
Secure, define secure. Which parts of security do you mean right now?
meaning that an attacker can exfiltrate private
If you get access to one party, then you cannot. Even though we give you an honest but curious security proof, then let's come back to what Kirsty suggested before. Even if you do your honest but curious protocols nicely, then even if you are maliciously in control of one of the servers, you cannot exfiltrate private information. However, you can always run one machine on Mac OS, one on Linux, and one on a Windows server if you don't control.
So I guess the answer is no, you don't do any diversification. But I mean, if you're running the same software on all 3 systems, and you have a vulnerability in your software, I mean, running on different operating systems.
I really can't see how I'm different from everybody else in this room.
Well, we don't use, I mean, if you're not using compute, like you're using compute units, you don't have the same issue. We're secure multi-party communication.
We may have to take the discussion offline, I will disagree on your premise there.
Okay, thanks, Andy. Okay, it's an exciting moment. So let's organize it this way. The winning team comes from the front, and organizers will deliver a certificate and a check. Thanks for human longevity for the general support to this event. We actually really can credit the winners with a real check. For the ceremony purpose, we printed a fake one. So Jonathan and I can hold the check, and the organizers can deliver the certificate. So the first team will be MIT and Stanford. And the other one. It's important to get a picture.
Yeah, okay, so this is the first winner, and the check is larger than the content. Let's play for more zeros. So which one? I want to profit because I promise I would announce that actually we are going to look for people working in this environment in the HLI. HLI is, it's the creation of Craig Venter to sequence 1 million genomes. So I guess we better worry about this problem together with you. So if somebody's interested to work with us, it's a position for scientists advertised in the website of the company.
Congratulations. The second team, Microsoft.
I did distance training.
Congratulations. So the third team is IBM.
I've always wanted to do this.
Thank you.
Congratulations.
It's the first time I've ever won anything, so I just want to thank my mother.
Now, Maryland. Congratulations. Okay, University of Virginia. Congratulations. The last team is from University of California, Urban.
Everyone will have an opportunity to. Actually, we should take a picture.
Right, together with this one.
Congratulations. So this is a fake one. The real one will be sent to your address. Okay, so the final session, we will do it really quick. So actually, Xiaofen, Shuang, and I will quickly conclude and think about what's the next step.
Okay, finally, we're already running out of time, so we're trying to quickly summarize what we learned from this workshop. And
I think the take-home message is when we are making progress toward this large-scale secure computing of real-world genomic analysis tasks, which is really exciting. But on the other hand, we are still there, right? There's gap in the technology. To narrow down these gaps, is a joint effort. I even just emphasize this joint effort from both bioinformatics, and cryptography, system security, and also bioethics and legal people. I think the key here is we need to connect cryptography technique with what the bioinformatics genomic research application needs to do. Right? We need to bring this to end. And one idea we're thinking about is potential infrastructure. With on my hand, we are doing this kind of competition structure that connect cryptography to produce the most efficient, effective, creativity, which geared toward the need from the bioinformatics. And on the other hand, we will communicate with bioinformatics researchers and to manage use this infrastructure. Right, and also in between, and what we're trying to do is we're trying to do this kind of this approximation because we know the limitation from the cryptography and we know the need from the and the biomedical informatics end. So we're trying to convert problems, that need to be addressed, and which cannot be handled by today's cryptography into the form which they can do. And so most important, the following issues, including we have this DMC special issue on human genomic privacy, and the participant in participant paper, and so again we will talk more about these things, right? And most importantly, we already have two competitions, which personally I think was pretty successful. So we are thinking about the topic for the next competition. So we can have a discussion on these, a quick discussion on these issues. What in your mind is, through this workshop, it looks like a lot of teams just complain they don't have time to finish their task, right? They have a better technique. They can build up faster, this analysis technique. And so, just maybe next time we will still have this, just an homomorphic encryption track, and maybe we also consider, maybe we still have this competition track, right? But also a new thing is, and I think it's very intriguing, people are using those, just at more than 2-party, just 3-party, 4-party, secret sharing-based approach. And those approaches, and on one hand, they can achieve, just a higher privacy standard. Sometimes, oftentimes they can achieve this information direct security, not based on any hard problem, right? Which is a good thing. On the other hand, they have this, just a non-moving assumption, right? Which need and then new legal framework to address. I'm so glad, from Estonia, you guys already have past the legal barrier, just already have this agreement, right? And it's very interesting, and it could be very useful to the other country, particularly for this country, right? So we're thinking about the possibility next time, maybe we can have a secret sharing track. Yeah, let people bring on those techniques based on this non-polluting assumption, right? And we're trying to run on the real genomic task and see if this can work out. And we'll also try to bring in those legal ethics experts to discuss how we're going to just have a legal framework and for this type of just analysis in this country. And so this time random thought. So I would be more than happy to learn from you guys. What do you think about this workshop, and what do you think about this competition, and just what will be the best topic we can do next time.
Actually, before proceeding to the audience, actually I want to say we are learning from the competition. From the first time to the third time, if we have the next time, we will do a better job. So by giving not only the instruction, but also publish some ground truth so people can easily verify. So this time we have a lot of back and forth because there's some communication and we didn't put a very clear explanation. So if there's any mistakes happened during the communication, we really apologize for the mistake. But next time we hope we can do a better job. So after this workshop, I will send out a survey, and I would like to hear what kind of improvement you would expect from us so we can do a better job.
And one thing is we really want to hear from you guys. How do you think about this competition, and do you have a suggestion for the next competition? If we really want to do another one.
Thanks. So first I want to say that I think you did a great job. Always there's going to be little wrinkles, but I really think that we should give them a round of applause for all their hard work. So I have a couple of suggestions. So of course I have a bias on the side of homomorphic encryption. I wouldn't necessarily prioritize that over other things that you think are important. Secret sharing sounds like a great idea. But with homomorphic encryption, there's so much room to run more complicated tasks or to refine the expectations in terms of the security model, or like you said, be more specific about the requirements, things like that. So I think, I mean, just off the top of my head, I think you could run a competition every year for the next 3 to 5 years just in homomorphic encryption. And it would get better every year, you would build a community, and you would see the results getting better and better. I'm not saying that's what you should do, because there's probably other things you might want to do, but I think there's plenty of room there, in my opinion.
Thank you. And I think it's very targeted.
So I think we're really missing threat models.
Oh, yeah.
And I'd like to have a whole workshop around threat models. And I know that might sound a bit morbid, but I think one of the hardest challenges that we keep running into every time we talk with program managers at the NIH and the NSF and DARPA and many places is that they keep saying, show us the bodies floating in the water. And it is really challenging to figure out what the solutions should be oriented toward, because we could work on 100 different things. And we can have competitions around lots of things, but I don't know if we know what specifically it is that people who are going to be using this data en masse are worried about the most. Yeah. So I think that would help to prioritize where things are going in the future. And maybe that becomes part of the task, but and I don't think we can have a whole workshop around threats, so I mean, I think a whole lot of it would be fun. But yeah, that's why I'd like to see some type of focus on.
Well, I would sign up for that workshop. That's actually why I wanted the microphone. So one thing I also noticed, particularly, this is probably a little biased in my perspective also. So I think you showed some really nice, really interesting account models. Good feedback I also provide, maybe a little more generalizable, especially as my esteemed colleague from Microsoft was mentioning, that this is could have a lot of longevity to it. You're focusing, in my opinion, on challenge problems that have more logical computations, like distance, things like that. Any things that might be a little more statistical in nature, which I think would be of high value to show the overall breadth and capabilities associated with homomorphic encryption. I think which might be a little more numeric as opposed to more logical type computations. At least what I would classify as more logical type computations. Thank you for organizing this. Very, very interesting.
Thank you. Suggestion? Yeah, I think, just a very interesting things, just come up with, and one possibility is, again, next time we can have multiple track with different advocacy model. Also invite, just the people from health practitioners and, the different stakeholders, so people can talk about what they work on. And the different advocacy model, we can see what the best we can do. But it is one possibility. I think before the end of the workshop, so I think we want to ask, there's a workshop, yeah.
So actually, maybe you can introduce, we have a slide on that. So in May, we have another workshop in conjunction with the Oakland conference. Brett is the program chair, and so this will be in San Jose, and we will cover similar topics of interest. This has started actually at Amsterdam last year, right? Yeah. Shogun was one of the organizers in the conference, and we are trying to continue this.
So maybe the accepted list of papers is already online.
Oh, okay, sure.
So last year we have about 40, it's 40 people attend the workshop. Last year it is with text. This year with Okana. And so if you attend Okana, you're welcome to attend workshop. Right? This is one of a kind. A lot of people are interested in these topics. It's a good place to meet the people interested in genomic privacy. And and that's a good place to showcase the technical innovation. Thank you.
Thank you all.
Yeah, I think that's the end of the workshop. Thank you.
We're right on time.
Yeah, you have to close that.
Everyone, we want to take a group photo. If you are interested in it, should I get together to take that group photo? Or I can suggest some. Okay. Yeah, just outside this building, you can take a group photo.
Nice to meet you. Yeah, same here. So, try to remember to send you an email.
Go back. You have some data, right? Yeah, it's about to be the yeah, I mean, between the 10. Don't like that now, so they are, I was thinking like, because this year we didn't dealing with so it's